Welcome everyone to Cloud Computing and Big Data, our lecture 1 today, where we have really again an introduction to cloud computing and big data, but also a little bit more deeper, right? The first prologue was more administrative. It showed you a little bit what the topics will be. Now in lecture 1, we clarify some of the key terminologies. So what is a GPU? What is a CPU? Everybody knows what a GPU is? Okay, what's the difference to the CPU? You know that? Okay, well, these are the things we will talk about, right? So, and these will be important differences, and the terminologies and these basic foundations will be reused throughout the course when we come to machine learning, when we come to deep learning and clouds and so on. Interestingly enough, that is also related to costs, right? So costs in cloud will be also with us the whole time. Of course, the more cutting edge technology you have, the more you pay, right? Especially for cutting edge GPUs. But before we dive into the material of today, let us review what we had in the prologue a little bit more. And this will be a theme you have throughout the lectures, that we always review a little bit what we have done the last time so that you get the connection. As I said, usually, welcome. This is something where you see that also many of the course aspects are sort of interconnected, and we will make the case for it. So the course motivation for cloud computing and big data can be in many different application areas. And we have seen that basically deep learning these days is a very popular topic, lots of jobs around it, and really a theme that can benefit from big data on the one hand, and also from the huge technologies that are inherent in cloud computing. Hence, we do a little bit of machine learning and deep learning here in the course, as you noticed, but we keep the, let's say, degree of mathematics behind it to a moderate degree, right? So you can learn this in Stain's course and other courses here at the university, the deep down details, how to really create a tensor from the ground up or so. Here we really rather use it as a case for using big data in practice. And we have seen this interesting diagram, as I was telling you, where you see that traditional learning models that you see on the lower level here still have relevance, right? They're very good, for instance, if you don't really swim in data. So in this area here where the arrow is, you can forget about the lines here, which says better accuracy with deep learning. If you don't have any data, so the data set volume is very low, deep learning has almost no chance, especially if you have largely deep learning networks. You can do techniques like data augmentation to enrich the data, to make it better and bolder, but usually you are better off using traditional learning models like support vector machines, random forests, and so on. However, when you go to the right side, you know, when you're swimming to big data, lakes, and so on, then you will clearly see that your traditional models have problems, especially if you use scikit-learn things on your laptop. They will not cope anymore with all the data because it has to be in memory, and the memory is limited on laptops, for instance. Hence, we will talk today also about memory in the course. You have to understand a bit that this is a key element in computing and fuels also, of course, the speed of computing significantly. But coming back to the diagram, you see the red footprint, which is now bringing also in the computing perspective. So the more you have this, you know, deep learning models elaborate, so smaller, then you can get up to transformer models, autoencoders on the large deep learning network side. You will see you have to have lots of computing power. And this is actually then shown by this red footprint. So this brings all together what we want a little bit to show in the course. Of course, then you see a little bit the cloud around the computing, and this is something where we talk also explicitly here in the course a lot, the scalability of that. While our HPC systems, things that I teach in the other course, are really solid, homogeneous, and standing there, in the cloud you have the possibility to go up and down with your needs. And we will talk about this again, about storage needs up and down. You can sell you know, parts of this, you can buy more of it if needed. And we talk mostly in the course about the three major providers here. You would say Amazon, Google Cloud, and Microsoft. But every now and then we go also to the European Open Science Cloud, which is an academic cloud provider for research. But also we'll make the case of local Icelandic providers every now and then, like Rescale, Borealis data centers, and so on. By this, we have also shown in the last course a little bit the ingredients that you really need to make a successful company today. We have seen one of the startups out of my research group, Soccer Watch TV. They really needed the big data. They recorded in 4K lots of games of soccer. They had then the hardware, they had lots of GPUs and the skill set to learn essentially from that. And luckily, they had the software for doing it for free, right? PyTorch TensorFlow is today just beautiful free. That's a perfect time. 10 years ago, my students had to implement this from scratch, right? So one of my master theses in the past 15 years was basically from one of my students, implement neural networks on your own in C, because there were no open public frameworks, right? And this in parallel could mean hell a lot of development time. We will talk about also in the course. And with this key ingredients today, many companies can really thrive because we see more and more quantities of data, cutting edge hardware available, and all the software frameworks are actually open source these days. Then the course organization content, I think by now you got the message. You get the, I think, messages that I always give you as reminders, or the course material in the Canvas. This will be our central element. Also for the quizzes, they will be in Canvas. The only thing that is a bit different is the add tool, right? This is a kind of discussion tool for those of you that don't know. That is related, however, to Canvas, and you can also click it from there. I have to activate it still so that you find group members and so on. There, and then finally, there are, let's say, two major, I would say, technologies we will talk again, which make this course a bit distinct from the HPC course. And this is Apache Spark and Hadoop. I think I already asked who knows about Apache Spark a little bit. Yeah, not so many. Apache Hadoop. The difference? Okay, exactly. This is also something we will talk about. Apache Spark, for instance, leverages memory a lot. And with memory comes speed. But of course, if you don't have a system with memory, all these advantages, are away. So this is another point where we will talk about hardware in the course again, combined with the software solutions, because they have to match, right? If you use Apache Spark on the system without memory, you're back to the Hadoop performance. And we will talk about this also in the NETA lectures. This will all come. So it was more an organization lecture of the course. Of course, if you have questions, you have seen the email from my assistant, please feel free to also arrange office hours if you want. Now coming back to our course, today is really, again, a sort of introduction, but also in the introduction sense of clarifying terminologies, clarifying technologies. So we have an interesting program today for us, thinking in the first part a bit about cloud computing in a more deeper sense, how it is constructed in a distributed fashion using parallel computing, how the internet is basically related to it, and also thinking about what are now the technology advances that make it possible to really compute big data in the cloud. And with this, we already said we will clarify many of the technologies here, like GPUs, CPUs, memory, and so on, and then come a little bit to also then the motivation related to it, right? Why people want to have infrastructure as a service, platform as a service, or software as a service. This is directly related to the hardware and software needs and requirements of companies, and we will talk about it in the first part. The second part is then putting the shift from computing more on the data side. Also there, cloud computing has a lot to offer. However, we first motivate a little bit what is big data. We have all sort of an idea that volume might be related to it, right? Big for big data. But of course, there are lots of different challenges. I told you once, for instance, we have some measurement elements in science and engineering where we have 1 petabyte, right? Karlsruhe is actually quite also famous in this area, right? So, but 1 petabyte per second is a problem. 1 petabyte alone is not a problem, but 1 petabyte per second coming in from this measurement device quickly runs for your storage devices. So we have to talk about big data in a different sense, not only volume, there's also, velocity, veracity, different V's and so on. And we talk about it a little bit. And then directly related, thinking about the limitations we have today in storage, right? So we would say again, petabytes, soon we have exabytes actually, for instance, in my center in Jülich with an exascale computer, we basically quickly fill our exascale storages very soon. But how you do deal with this on the different storage hierarchies. I mean, some of you have maybe heard from tape archives. So there's not just disks, right? There are tape archives where lots of petabytes can be stored, but they're extremely slow, right? So when you want to compute on it, you have to migrate things out first and then compute on it. So we will talk about the speed of storage related to this and the storage hierarchies. Of course, disks are somehow in the middle between memory and then the capacities that we have in tapes. And that's why we call this a hierarchy. We talk about this. And then, of course, one of the ideas of cloud computing inherently in the second part, which is this kind of scalability notion. right? You have this dynamic character of adding storage quickly if you need it, swiping the credit card, or basically if you don't need it anymore, you can get rid of it very quickly. That is a key ingredient of cloud computing, not only in storage, but also in terms of computing. And then we end a little bit today with big data analytics and machine deep learning, relatively high level explained, so that we can dive, as you will remember, lecture 2 is already machine learning models in clouds, more in machine learning in the next lecture. So let's see, foundations of computing in terms of clouds is something where here and there, I think you definitively know already what's happening because you're using these systems daily, right? You use systems, cloud, who use Google Docs, for instance. Almost all, or I mean, almost everyone has seen similar services, even if it's just like Microsoft 3086 or whatever. So mostly it's fueled by services, right? That are somehow giving you a very, let's say, seamless access. You would have just your laptop, a very thin client, as we call it, and then you have a very powerful entity that we now call this cloud that you can access, and has all these different elements like hardware, storage, and so on in it, several software solutions, and they're all on different levels. And hence, the cloud community really did this in the beginning for free. We called that a little bit like grid computing, right, 20 years ago. And over the time, basically, this became much more commercial, right? So more and more commercial providers came along and created these clouds in the internet. Google Docs was formed. Who knows Google Beta still, right? I was in the time of using Google Beta, the search engine. That was just coming up, right? So these were all things where Google Docs was not there, right? So this was all suddenly coming. And of course, then the idea of these providers was paid services. Hence, so one of the key ingredients in clouds is, of course, you can have lots of requests, which is the abstract, let's say, term for it. And then if you swipe the credit card, you can get really good paid services. Another aspect of this slide should show you also the abstraction from it, right? Some of you know from the HPC course, you were much more lower level. You know exactly how the system will be. But here you sort of have an abstraction level of hardware where you don't really need to know the very deep down details. That's only half true. The full truth is you still need to know it's lots of memory here. Is it a GPU? Is it a CPU? But you don't know the whole network architecture, how it is interconnected, how much bandwidth this has between the different nodes and so forth. So lots of, let's say, technology details are inherently abstracted away in clouds. And that makes it a bit different from HPC. Then also as a first one here, the introductory lecture will reference now many of the following lectures, right? Again, it's an introduction lecture. We talk about many of these things much more. For instance, in lecture 4, how we would build such a data center then, and how we make it then so scalable to make, let's say, the possibility to remove and add storage every now and then. So cloud computing, as I was saying, come from grid computing using parallel and distributed computing in the past. So this was really something which was really not starting overnight. It has a long history, but there were also, let's say, 2 established computing paradigms that a little bit were driving this activity. And these are paradigms that stand the test of time. That's basically, they're called paradigms. And that's why it's also important to understand them. So high performance computing, you can imagine, is something that you see there, very nicely interconnected between all the nodes, very homogeneous. There's one system somewhere, maybe even a large data center system, but it looks sort of, you know, very tightly integrated. Now, high throughput computing was around since many, you know, decades also at the same time, but don't think about much more homogeneous, but using different servers that are there. And the idea is there not really to communicate a lot. So you will see a little bit the network interconnect that you see here on the slides is one key ingredient of the difference. In high throughput computing, you want to be independent, you know, working on the data, maybe independent, and just then do some summary statistics in the end. In high performance computing, we usually always interact between the different nodes. There's always communication going on, each iteration and so on. Hence, these are 2 different computing paradigms that will basically also always remain. And this was driving a little bit the idea of clouds, because HPC centers have been around also since a long time. But the high throughput character of combining all the resources to one, let's say, cloud, that was not the cloud term yet, but this grid idea to connecting all of these, let's say, smaller boxes, if you want, from computing that are sometimes idle, wasn't something also fueling the cloud in the beginning. Just again, a little bit the HPC and HTC difference. So we're doing in the cloud course much more on this level, on high throughput computing, but it's important to understand the difference that usually HPC systems are much more, having a very good interconnect, and that's why the HPC systems are also so expensive. Here we talk about InfiniBand connections, not Ethernet or something. So they're very optimized for message exchanges within the computer, right? While HTC could be, one node is here in Iceland, another one maybe is somewhere in Denmark, another one might be even in Germany. We don't care about the speed. We just offload, then it computes his thing. And at some point in time, I'm collecting, the summary. Of course, I want to know maybe a summary or something at the end, but I don't have this communication like in weather forecast, right? Every iteration of predicting the weather every minute means lots of exchange of physical variables if you compute it with physical laws. So hence, this is more weather forecast, physical modeling, car crashes, while here in high throughput computing, you have much more working on documents and elements like that. Of course, today there are also clouds that give you a HPC system access, but of course you also have to pay for it. And usually it's also not that you have this on a large scale, right? Like really now an exascale center or petascale center that we have in Lumi or so. Here you see a little bit the evolution over time. I think it's also important to understand that these paradigms really formed different elements. We have seen this also in P2P networks coming out of HTC systems, while we in HPC much more often were really in homogeneous multiprocessor entities. And you have seen many times, I guess, always these kind of characteristic images of HPC machines, long corridors with lots of similar hardware. While then the idea of doing it geographically dispersed meant also that these hardware boxes can be different in nature. Let's say you have a couple of Volta GPUs, you have a couple of Ampere GPUs. You don't mind so much in this area of HTC. The important thing is that they may be idle and you want to use them, because if they're idle, that's just waste of resources. And from this, the whole idea of this data grids and computational grid computing, which was the predecessor of cloud computing, emerged. And from this, basically, then different elements came out, a little bit Web 2.0, so everything we see now, much more nicer internet websites and so on, but also the Internet of Things, which is one of the, still research now, which is also actually done here at the university by ESA. If you're interested, we have, I think, also a course around that. But this was fueling different angles to go. And of course, also in the internet clouds really commercialized the field, which was now very important, because by now, I think everybody of you who uses Facebook, there's also a funny question in Iceland. Even my grandmother-in-law uses Facebook. Yeah, with 95 years. So this is sort of a religion in the country. And this is just an example. In a way, it's a perfect example of a cloud that works. We have others like, that are more specialized, Salesforce, or here we have a very specialized one, UberCloud, which was recently bought by SimAir. But the idea remains that they specialize just for engineers, basically, and researchers, instead of, basically Google Docs, which is for the general audience or for the general public for almost everything in documents. You see, everybody has its own, let's say, value proposition, why people would pay. One common theme is also two things, essentially. They're all interested in your data, right? So Facebook, especially, learning from data, right? Machine learning and other things. And then the second is really thinking about, once you have that data, to accumulate it and to work with this and make money out of it with different perspectives. So in this sense, you will see many of them have this kind of hook character. Like Amazon will give you free credits for computing, will give you, a free profile in Facebook here. You can use mostly these clouds initially always for free, or at least partly for free. And once you're hooked in the services, then you basically, we call this also vendor locked, right? You're basically bound to this. They kind of starting with charging something like this. You will experience this. If you use, for instance, OneDrive, I don't know, it's a Microsoft solution for storage. You can have 1 terabyte for free or 2, family sharing, etc. When you then end up with your whole, whatever, MP3 collection or whatever on data, you're suddenly in the more, let's say, 10 terabyte regime. And then suddenly there come the credit card swipe. And this is a common theme in all of these cloud computing elements, because it's a huge competition also. And once you crafted, for instance, your services on Amazon, have lots of different services used in Amazon, it's actually not so trivial to just jump to the Microsoft Azure cloud, because many of the services are, sort of speak, very specific for the cloud. And in order to, let's say, get the customers and hook them, they have always this kind of free offerings usually. Now coming a bit more to the terminologies again, because many of you maybe don't really have used parallel computing in the past and don't really understand what centralized computing might be in this area. So here we have really different areas where we think like all computer resources are really in one physical system. That is rather what we call a centralized computing system, right? Your laptop is one, etc. But the clouds are really optimized for parallel processing, parallel computing. We have seen on Tuesday, the video, if you remember, from Amazon, right? They have geographical locations all over the world to serve the customer as fast as possible with data in and out and so on. And instead of going to the US, there are also Europe nodes in AWS, for instance. So, and this is all enabling also parallel computing then, when you have different computers to share, right? Which is basically the idea here of this centralized computing, not really so easy on a broader scale. Of course, parallel processing in HPC is also one key ingredient, but you rather would think it's basically on one application and you would use it still within one HPC system, right? This parallel computing application. Here we will learn with Hadoop and Apache Spark that you can actually go across different, let's say, boundaries of the hardware and include maybe, let's say, 5 different locations with Hadoop nodes or with Apache Spark nodes and so on. So this is a little bit the idea there. And which is important, that is also, of course, covers a bit the storage ideas, right? So having parallel access to different disk data is also an important part of it. Hence, we will talk in Hadoop also not only about computing and this map reduce I was showing you, I think, in the prologue, right? With the divide and conquer strategy, we also talk much more about what we do with the data. There's a Hadoop distributed file system even. Yep, there's a question. The question, yeah. So can we see that parallel computing helps to implement centralized computing? That's partly true. You have to see on which, let's say, level it is really, right? When we do centralized computing, we have distributed memory, shared memory programming, things we do in the HPC course, not here. It's also one form of parallel programming, right? When we go, however, for Hadoop, we have parallel computing and parallel programming on a much bigger scale. We would leave the system that we have in front of us and don't care actually of, sending messages one-to-one. The Hadoop engine, as we will learn, will take care of that automatically. Also, if it fails to actually use something in parallel, a node fails, it will resubmit to another node. It has many of these fault tolerance elements in it. When a HPC system has a little bit of parallel computing and there would be one CPU, let's say, out of service, then the whole application goes down, right? So there would be errors. But the terms, of course, are intertwined with each other a bit, but there is this big difference on the different levels. But I think we will see that over the time in the course, when we come more to these examples, what we can see then basically there. And of course, parallel computing will be a key essence and also in the HPC course for those of you that are interested, but on a much more lower level. Hence, when you do this parallelization to the extreme, you come to this term like distributed computing, which is then, that's what I was alluding to. Parallel computing really in the cloud. You use maybe even different devices for it, because often even some, let's say, devices for measurement can compute or pre-process or post-process some data. So this is something also what you would include. And for this, you have, of course, now different orders of magnitudes of challenges. When you have just parallel programming inside the computer, you don't have to think about security, right? You will see MPI, for instance, the message passing interface that you use there is very terrible in security because it's not needed. It's protected within a HPC system, but enables you to send messages, to do parallel computing on a lower level. Now, once you reach the higher level, and to perform distributed computing in parallel, then you add a lot of different challenges to it. So you cannot just use, for instance, an MPI now and putting it over TCP connections or over HTTP. You need security. You need basically accounts on different systems. There's a whole kind of worm which makes it really much more challenging to have then these cloud computing systems alive. And we will talk about this also when we think about different Hadoop nodes later in the course. And a good example in the beginning was for this cloud, let's say, theme, the Boeing. I don't know if some people have heard for it, Boeing infrastructure. So it was like free, let's say, desktop computers could be added. So you can basically donate your computer into the cloud, your personal computer at home that is maybe idle, so something which is not used or overnight, and contribute to scientific, let's say, computings that is done. You see, it was even used in COVID-19 recently, the whole Boeing infrastructure. So this is example, let's say, from the bottom up, where it's not one guy buying a big HPC machine, putting it somewhere in a cellar or in a data center and operate it. Here, the idea was volunteer computing. So people that would donate their system every time it's idle. And the Boeing infrastructure was use these idle resources whenever it's free, or basically you say you can use it. And this was one of the first sort of cloud ideas, free of charge, of course, and so on, fueling already the idea of this geographically dispersed computing power in different orders of magnitude, small boxes. People have actually overnight at the university, some of them I teach very early, the whole workstations were contributed overnight, right? Because the students were just using on the day just to contribute to these elements. And this is, of course, an interesting idea. At that time, it was very, let's say, academic driven. It still is academic driven, but fueled also many of the ideas that we have today in the cutting edge cloud providers. So coming to Amazon Web Services, and again, you can see in lecture 8, we will talk much more in detail about it, right? Of course, it will be the whole lecture just on infrastructure as a service. But Amazon here now as an example, MS Azure has very similar services, has now the idea that you have this interesting EC2 resources that you have somewhere. You don't really know where it is. You can in Amazon steer the geographical location if you want, but you don't have to. But this means inside this cloud would be this EC2 computers. There are different types of them. You can actually choose them on the list, which one you buy and which one you want to rent more or less. And they are related to, for instance, also storage resources. We talk in part 2 of the lecture today, the S3 interface. It's a very, let's say, almost de facto standard today of storage. And that you probably have seen, I was alluding to Gradescope is one service, for instance, that UCS3 service here at the university. And then you can essentially shrink up and down the needs while you want to do it. And you can pick different types of resources, so GPUs, CPUs, and so on. And we talk, of course, in lecture 8 much more about it. But one key message to take away is it has some, let's say, security elements already, right? Beyond firewalls, there's accounts. We will basically together work on a resource group in Microsoft Azure that I have to give you access to. So there's lots of authentication, authorization, security elements inside, which you would have not in a HPC course on the lowest level. So here are really lots of services also, I should say, right? So this is really one of the very fundamental services to make it a bit, rudimentary on the IAAS level. So, the infrastructure as a service level. Once you go higher in the levels of the services, you will see that there's also much more, let's say, powerful services. But the point is they are stacked on each other, right? Even if you have a platform as a service, a billing service, it has to run somewhere, right? Whatever service you buy on the higher level, it has to run on some computing node, right? So in the end, you automatically rent the underlying infrastructure then as well. Hence, we have a sort of layered approach of saying infrastructure as a service is the lowest layer. And then you would add a bit the platform as a service character. And then on top, would you see the software as a service character. However, of course, they're intertwined and use each other significantly. But while seeing this, it's also important to understand the different technologies quickly here. I think this is a multi-core CPU. So here the idea is that you have many different cores, multi-cores, but not many of them, just a couple of them, because they have a high clock frequency, so a very high heartbeat, if you want. They are number crushers, very good performance, very high let's say, single thread performance, you would call it. And you have a couple of them, and you cannot put more on the chip because the chip would be, overheated. The benefit of the CPU on top is that it has lots of cache hierarchies, right? And cache is very, let's say, one of the most fastest in storage you can have, but also the smallest, right? So unfortunately here you cannot put petabytes in. So these are all examples where you would say, okay, that is characterizing more or less a CPU and makes it now different from actually the GPU, where every, let's say, core you have in the GPU is moderately, in terms of speed. It's just, let's say, not really high clock frequency, but the benefit is you can put very, very many on the chip, right? This prevents the overheating and is fueling now all the advantages of NVIDIA. And the power there is, again, high throughput computing. You would do in this significantly. We will talk about this also later in the course a little bit, in the HPC course much more. But here the idea is that you put really hundreds to thousands, let's say, very simple cores on the chip. You remove some of these, let's say, cache hierarchies. Instead, you have something called device memory. And the device memory, again, needs to be fueled from the main memory of a CPU. Hence, a GPU cannot be standalone, right? It needs always a CPU to operate. So that is one of the most, let's say, drawbacks these days, that when you have data, you always have to load it to a CPU and from the CPU into the device memory. And this is quite a bottleneck that we have today in computing, right? So this is something which also prevents much more higher level, let's say, operations on data. But this is now the differences, let's say, on some level of detail. We could go much more into detail, but we leave it here in the moment. We come later to more, let's say, examples between different architectures in the GPU regime, from Kepler, Volta, and Ampere to now what we have is Grace Hopper cards in NVIDIA. They have, of course, lots of different advantages. But I hope you're with me so far. What's the difference between CPU and GPU is, right? Otherwise, raise your hand. Good. You two also okay? Good. I hope the evening was not too long for you yesterday. Good. Coming one layer up the stack, right? Infrastructure as a service, very basic. Bare metal, VMs, computing, a little bit really storage facility. Now we want to go one level up, which means we need so-called services that enables us something. The platform, however, is not a fully application, right? The idea of the platform as a service is, I think, quite nicely characterized by Lego blocks, right? Each of the Lego blocks has its specific functionality, sort of color. And we have the same in the Google Cloud, for example, on the platform as a service level as well. If you want to create an app, and we will talk about these apps a little bit in this course in lecture 9, how people are using it to combine different Lego pieces now inside the cloud to actually then create your product. And with this, you have the app engine from the Google Cloud, which is quite good. You can scale up, scale down, which is again characterized by our cloud in terms of data or compute. Use the Google Cloud for it. But of course, it is all different elements of, traffic monitoring, how many users you have. Do you have to scale up with your storage needs? Maybe too many users. I was giving you in the prologue the example of the Angry Birds, right? Which was suddenly was, going up to the sky with the usage. And before, with their soccer game, they actually had a complete failure. Nobody wanted to use it. So this is something you don't know, right? It's not foreseeable. And suddenly you're successful, and then you can just grow with your applications by leveraging this. And of course, there's a whole development cycle. For those of you who are doing software engineering here with Matthias Burg or so, those software engineers, okay, one. There's a whole development cycle, right? So versions of the app, the dependencies and so on, which is also nicely, let's say, available in this cloud. And the whole idea of also deploying this regularly to the cloud, keeping it maintained with versions and so on. But yeah, lecture 9 will talk much more about it. And it's of course clear, as you will see here, particularly in this part, it is platform as a service with all higher level services like development services, the app engine, hosting, and so on, the interfaces. But lower level here is still infrastructure, right? So hence, the platform as a service uses the infrastructure as a service on top. And now when we come to the highest, we have first an example, yeah. So I think Angry Birds was an example already was saying in the prologue of the course is something to look at. Just some numbers, I think, is also important to notice when you're a small SME and suddenly confronted with many millions of downloads, how you do this, right? And of course, many people will use it at the same time. Then you need in-app purchases. So you need the functionality that people swiping the credit card. You have to implement all of this if you don't use these platform elements, right? And this is not easy to implement. You need agreements with different credit card providers, et cetera, et cetera. Here, basically, you get it quickly done. There's a nice case study here that I also linked you. It's a full description how Rovio and Angry Birds actually benefited from the Google Cloud in the references. And we talk, of course, in lecture 9 much more about it. And it's just one of the, let's say, well-known examples of many. They have lots of case studies actually on their website. Now coming more to the end of part 1, we have reached the top, right? In a sense, in cloud computing, and that is what we call software as a service. So here the idea is not anymore developer-oriented like the platform as a service character. Here the idea is really using the software as is with your data. Right? Of course, Facebook and all of that would be equally examples, right? You don't program anymore big in Facebook or something. So here we talk about different systems and services which are already ready, deployed, and used. And lecture 10, of course, will make several examples of it. Here I pick one which is related again to machine learning and basically a new service called SageMaker, which is quite successful in creating cutting-edge models. But also, this is a good example to see it has all to do also with the underlying infrastructure, right? It's a beautiful service. It tracks your runs in machine learning. And I know that everybody, if you doesn't know about machine learning yet, we will talk about this next week more and then get an introduction a bit and also later in this lecture. But this would be one service that you can nicely use and do very nice modeling. Let's say you're an SME. But of course, when you do cutting edge modeling, you have to go and pay the price for it. Right, SageMaker, if you want to use it on a daily basis, is quite significant of expenses. So you want to incorporate this in your products, right? So every time the app is downloaded, don't think about maybe €5 a download, rather think about 10 or 20 euros of a download, because you have to incorporate your infrastructure usage as well in the cost, right? This is another thing we will talk about all over the place in the course. And of course, it's related to which extent you now use the IAAS and PAAS services. So do you use cutting edge GPUs and it's much faster? Or you use, let's say, very old, on the spot elements, and then the GPUs will be maybe slower, but of course the price will go down significantly. Another facet in this, and also for your assignments, will be Jupyter. Have you used Jupyter notebooks before? Almost everyone. Excellent. Good. Though this will be also something that we will use a lot in the cloud, and which is important then to understand. But I see we don't need a Jupyter introduction anymore. In previous examples of the course, I always did a Python and a Jupyter intro. But as I think Ingolf has now a course teaching Python and so on, that was something where we thought we can leave that out. But he has then, of course, very much examples and so on his slides if you need them. And this, in a way, concludes already the first part of the lecture. I would just give you a very short video, which is, I think, a good idea to understand cloud computing again from different angles.